Well, thank you for inviting me. I would like to thank mainly some of my co-authors, especially Elisenda Bakker, who's also in the room, Ronald Pijnenburg, and John Samuelson, who have done actually the real work here. And it's quite a vote of confidence that they let me have their data to present. So I'll give it my best shot today. I quickly will explain the importance of storage integrity, and especially how chemical interactions between the CO₂, the brine, and the rock will affect some of the mechanical properties of the rocks. And then I will discuss how some of these processes have been observed in relatively short time scales, so in the lab, on clay-rich seals and faults. And then I will move over to more long-term processes where we've studied some of the natural CO₂ fields, and especially in this case, Green River in Utah. So here's a schematic of a CO₂ storage site, and you can see here this is the reservoir, this is the injected CO₂, and this is the caprock. Now when you inject CO₂, you will increase the pressure again in this reservoir, and as a result of that, there will be a poroelastic response of the reservoir. So basically it will expand slightly, and if the CO₂ starts, or when the CO₂ starts to dissolve into the reservoir brine, it will create an acid environment, and as a result of that, the reservoir itself may become chemically weakened by the injection of the CO₂, and that may eventually lead to compaction of the reservoir again. So when you think of it in terms of what will happen to the overlying caprock, basically you've got a system that will go up and down, and as a result of that, there will be some flexure of the caprock that may lead to permeability development at the base of the caprock, or in the worst case, maybe even failure of the caprock. That's not something we really want. Now, also, if you have any faults in the caprock, either bounding it or going through it, if you have enough flexural bending, or if your injection pressure is too high, you may actually reactivate some of these existing faults and maybe generate some slip. And the question is is that in any way enhanced by the chemical interaction of the rock with the CO₂, and will we therefore create leakage pathways, and will that result into a loss of containment, which is something we definitely don't want. We want it to stay there. The CO₂ needs to stay there for at least 10,000 years. Now, some of the chemical processes that have been identified are, number one, clay swelling. Hence my question. It has been known that smectite clays actually swell when there's water in the interlayers between the clay platelets, and when you inject CO₂, there's an additional swelling effect as well. So that is something to keep in mind. In addition to that, experiments have shown that microcracking is affected by the injection of CO₂, mainly because of the lowering of the pH of the fluid that the rock is in contact with, and it either may inhibit microcracking or it may enhance microcracking. Now, thirdly, there is, of course, the enhancement of pressure solution or other dissolution effects, where the kinetics of that process are determined by the pH of the fluid. So if you change the pH of the fluid, you change the chemical equilibrium, you may enhance dissolution or pressure solution within certain minerals. And then thirdly, some minerals have the tendency to actually react with the CO₂, forming new minerals. For example, if you have feldspars and clays, they can turn into kaolinite, maybe some carbonates and some other phases. But the main point there is that it's all depending on the type of mineral that you're looking at. It will happen on different time scales, also depending on the mineral, and the extent of these processes really depends on how much water is available in respect to the amount of rock that it's interacting with. So now I'll show some of the short-term results that we've obtained in the lab. So this is work done by Elisenda Bakker, and she's been looking at the opalinous claystone, which was obtained from the Monterey site in Switzerland. We consider this rock to be an analog for quite a number of caprocks present in Europe, which may potentially cap CCS sites. The composition consists roughly about 10% quartz, 70% of clays, and about 20% of carbonate in the form of calcite. Now, she did a number of shear experiments, which is nicely illustrated here, where we have these L-shaped blocks, and in the middle there's a simulated fault gouge, which basically is just ground up material. Now, we can put that under a confinement, and then we can start to slide these blocks to simulate slip along a fault like that. Now, she did that for a range of different conditions, both dry and wet, and at the same time she also managed to measure the permeability of this material, both along and across this fault. Now, there's one thing that I would like to explain. So these results are often explained in terms of friction coefficient, which is basically the amount of force that you need to move a fault, but also in terms of once the fault is moving, how does it depend on the velocity that the fault is moving at, which is called the velocity dependence, of course. So if you have a fault that's moving at a specific velocity over here, and you increase the velocity at which the fault is moving, there will be an instantaneous effect, like this, and then as it decays away, it'll reach a new steady state. Now, if this steady state is actually higher than the initial one, we call this a positive A minus B value, and that's good. That means that slip is being stable. Now, if you do that again, and actually after the velocity step increase, you come out at a lower value, so A minus B is negative, we call that velocity weakening. So all you need to remember from this story is, if A minus B is bigger than 0, it means sliding is being stable. If A minus B is smaller than 0, then there's a potential for unstable sliding, so perhaps some induced seismicity. Now, we wanted to know the effect of CO₂ exposure on the mechanical behavior of these opalina shale fault gouges. But since it's mainly consisting of clays and quartz, it's reacting pretty slow, and we don't really have time to sit in the lab for that long. So we set up a collaboration with John Kazuba from Wyoming University, and he performed a few chemical modeling efforts for us with the original composition of the shale, right here, and how it will develop through time. Now, we assumed actually some sort of a, you could call it a worst case scenario, where the fluid is actually moving pretty rapidly throughout the fault. So it's a lot of fresh fluid is being brought into contact with the rock, and you have the maximum extent of reaction. Now, overall, you can see that chloride and smectite seem to be removed pretty quickly, but they're also present in small quantities. But if you look at the more stable minerals, so the rest of the clays, the quartz and the carbonate, they actually remain pretty long, and they will only be removed at a very late stage. Now, that is actually good news, and the one thing that we're interested in is what happens if you remove all the carbonate, because one of our other colleagues, Bart Verberne, he's been studying pure calcite gouges, and he's seen some interesting behavior of this material with temperature and the presence of fluid. Basically, if the temperature goes up, you go from stable sliding towards unstable sliding. Now, I'm going to put in a quick plug, because last week he published a very nice paper in Science, and he basically managed to explain his behavior by the formation of what is seen here. These are nanofibers of calcite grains, where all these little particles are sintered together and form these really long fibers, and these are actually what make up these beautiful mirror faces that you can see in carbonate faults. So if you have time, check out his paper, and if you don't have time to read it, it has some really pretty pictures in it. But basically what we wanted to do is we wanted to indeed make this worst case scenario. What if we remove all this carbonate that has this funny behavior? How will the opalina shale then behave? So this is a summary of the behavior as measured. So we've got on this axis the friction coefficient against the amount of displacement. In red, you see the behavior when the material is dry. So it has a friction coefficient of about 6. And then as soon as you start to add water, there's a drastic drop in the friction coefficient down to about 0.3. And if you remove all the carbonate, you've got an additional weakening by about 10% of that. So overall, this material seems to show behavior that's typical for clays. And if you look at the A minus B values, we're all very happy because they're all in the positive regime, so sliding is stable. This is good. Now, Elisenda also tried to measure she didn't try, she actually did that. She measured the permeability of these simulated fault gouges, and she measured it both across the fault and along the fault. Now, actually, along the fault is the one that we're most interested in, because that's where eventually the leakage pathway will be created. It'll go up the fault, not through it. And this is a summary of our data. So we've got on this axis the permeability against the normal stress that's applied across the fault. And you can see these are the initial values in the solid lines, both along and across the fault. And you can see that as slip starts to occur, the permeability of the fault decreases strongly. And actually the difference between the across and the along permeability is about an order of magnitude, which is quite significant. Overall, the more slip you generate, the more loss of permeability you generate, and the higher the normal stress, the lower the permeability as well. Now, if you think of permeability of a fault, and you know that in the presence of certain clays, these may swell in the presence of CO₂, you start to wonder, since that the opolinous clay zone has some smectite, which is known to swell in the presence of CO₂, how will that affect the porosity and the permeability? So these are measurements by Sander de Jong. It was published this year. You can see that with increasing CO₂ pressure, there's quite a significant increase in the amount of swelling that's occurring in pure smectite. So up to 2.5–3% of strain is measured there. But what he also noticed is that it very strongly depends on the amount of water that's actually present in the interlayers. So this is the amount of swelling strain, and this is the amount of water that is present in the interlayers. And the most ideal state is really if there's only one or maybe two layers of water in between the clay platelets. So if indeed there's swelling by about 2–3%, is it possible to close up any cracks or any porosity and therefore reduce the permeability of a fault? We don't know yet, actually. What we are currently looking into is the forces that are generated by this process. So indeed, if swelling occurs and it does close a fracture, how much stress is being generated by that? And that's actually work by one of our PhD students, Miao Zhang. And he's measured quite significant forces of tens of MPAs. So it could actually be quite a significant side effect of CO₂ injection. Now, that was a whole story about faults, and we've also tried to investigate the behavior of intact caprock. The problem there is that low permeability rocks show very slow drainage behavior, and as a result of that, you will have not a uniform pore pressure throughout the sample during the experiment, which makes the mechanical experiments quite a challenge. So what we really need to do is we need to be able to decrease the drainage pathway of our samples. So here's again the direct shear assembly as used for simulated fault gouges, but what if instead of a paste of fine-grained material, we put a slice of rock in there? Are we then able to measure the mechanical behavior of this thin slice of rock, which will be about only 1 to 2 millimeters thick, so it has a very short drainage pathway across the sample. If we then slide this slice of rock, we will be able to measure the strength that's needed to do this, and at the peak, that will be the point of failure. So we can determine how strong the rock is in this configuration. So we've started doing some experiments to prove if this is actually going to happen. First of all, is the drainage actually improved? So one of our junior researchers, Ronald Pijnenburg, he's done the experiments for this, and he's measured the strength of dry slices of opolinous shale and for wet slices of opolinous shale. You can see, again, the same very strong weakening due to the addition of water. And from these experiments in the presence of water, you can see that using different pore fluid pressures, he actually got pretty much the same result. So that showed us that actually drainage is definitely improved using these very thin wafers of rock. Now, this is a picture of one of these wafers after the experiment, and you can see here some gray, light gray zones, and then in the middle it's a little bit darker. And basically, when you look into detail, this is the pattern of fractures that's formed. And we think that the boundary shears that you can see here are probably formed during this stage of the experiment, but these inclined fractures are actually going to be formed right here in this stage when the material is actually breaking. So when you look at the fracture angle there in respect to the maximum and the minimum stresses on the sample, it's roughly 20 to 30 degrees, which is very typical for rocks. So that looks pretty promising as well. Now, what about the strength? Is that also going to be comparable to experiments on plug samples? So here we've actually used data that was obtained by the Monterey laboratory, and we've plotted it in Mohr-Coulomb stress space. So this is the shear stress, and this is the effective normal stress. And you can see that these different circles, the green and the red ones are dry and the blue ones is wet. the green and the red, they actually seem to match up pretty well with this dry outlined filler envelope for dry plugs. So it's starting to look promising, even though we need to look into it a little bit more detail. But the question, once we get this to work, can we study wafers that are obtained from a real fault zone, so that have like a fracture already in the middle? Or can we react rock wafers with CO₂ and then study the strength afterwards? Because now that's still really difficult because the reaction times take so long and also the penetration is very slow. So one other way that we try to investigate the, 2 minutes, wow. The long-term effect of CO₂ interactions in caprocks is using CO₂ fields, natural CO₂ fields. So in Utah, there are quite a number of fields, and they've been exposed for very long times already to CO₂. So in collaboration with Cambridge and Shale Global Solutions and Utah State University, we set up a drilling project right here. This is Crystal Geyser in Utah, and we obtained some core through the Entrada Reservoir, the Carmel Caprock, and the Navajo sandstone. And it's really nice to see this contact between the reservoir and the caprock. You can see this bleached area right at the base of the caprock, and then it slowly starts to move into the unreacted material. So CO₂ penetration has really only happened for about 5 to 10 centimeters, which suggests that it's diffusion controlled. And the main thing that was observed is that the hematite content has been removed. So all of the hematite has been leached out more or less. Now, we did some shear experiments on that as well. I'm going to go over it really quickly because I only have 1 minute. This is the results for unreacted caprock there. So we've got a friction coefficient of about 0.6, which is quite high for something that contains about 80% of clays. A minus B values are all positive, so stable sliding, that's good. And the interesting part comes when we go to the reacted material. This material is reacted but still has about 0.2% of hematite. You can see still a friction coefficient of about 0.6. But when you remove all the hematite, it all of a sudden drops to 0.4, which was something that surprised us a little bit. Such a small difference in chemical composition, giving quite a significant effect on the friction coefficient. So the question is there, does hematite, even in small quantities, affect the frictional behavior of faults? So that's something that we're going to still look at in the future. But overall, I think we conclude that there are quite a number of different CO₂ brine rock interactions that can affect mechanical properties. They all depend on the type of minerals, the time scale, as well as the water-rock ratio. For most cases, we don't really see much exposure, not even if we try to model it in a worst-case scenario, and therefore there's not really much effect on the frictional behavior. So it is suggested that the frictional behavior of unreacted clay-rich rock can describe actually the frictional behavior of CO₂-exposed rock. And maybe sample variability may be more significant than the effect of exposure. So that's it. Thank you very much.
So thank you, and we have time for at least one question.
Uh, 1 to 2 millimeters.
So do you think that you can prepare a wafer of that small thickness and measure mechanical properties that are representative of the in situ?
Yeah, we think we do, yeah.
If by combining sequestration with gas recovery, the carbon footprint of hydrofracturing Reichel and negatively the political balance would shift in Europe?
That's a really difficult question because actually, from what I know for the Netherlands, where I'm from, a lot of the CCS projects have actually gone down the drain simply because of public opposition. So I am not so sure if there's going to be a beneficiary effect of any economic advances there. People just don't like it.
All right, thanks again, Susan.